Welcome to Engineers Mindset. Alright, to follow up our series on thermal stress. Now let's say we have a problem on the board which says a steel bar is placed between two copper bars, each having the same area and length as the steel bars at 15 degrees Celsius. At this stage, they are rigidly connected together at both ends. When the temperature is raised to 315 degrees Celsius, the length of the bars increased by 1.5 millimeter. Question says, determine the original length of the bars and final stresses in the bars. Take Young's modulus of steel as 210 giganewtons per meter square, Young's modulus of copper as 110 giganewtons per meter square. Thermal expansivity of steel as 0.00012 per degree Celsius, and that of copper as 0.0001755 per degree Celsius. Alright, so let's first of all bring out what we have. Let's try to make sense of the diagram. So we have a steel bar that is placed between two copper bars. So we have copper, and then we'll have copper, then we'll have a steel bar. This is what the idea looks like, okay, the diagram looks like. And he said from the question, they have the same length as the steel bar has the same length as the copper bars altogether. So let's call this length L. It was not given, so we are asked to find it. So let's get the parameters that we have. We have the initial condition of the temperature, the initial temperature. Okay, which is T1 was given as 15 degrees Celsius. Okay, at 15 degrees Celsius. So T1 was given as 15 degrees Celsius. Okay, final temperature, which is T2, was given as 305 degrees Celsius. So we have 315 degrees Celsius. Okay. What else is important? Okay, having these two, okay, we are given the increase in length by 1.5 millimeters. So there was an increase in length of the bars. When the temperature was raised to 315 degrees Celsius, there was an increase in length of the bars. That increase in length is what we call a change in length. So change in length, which is delta L, change in length, that delta L is simply 1.5 millimeters. So we can convert this to meters, and we have change in length to be 1.5 by 10 to the power of -3 in meters. Okay. Alright, so we are given the Young's modulus of steel and that of copper, and then we're also given the thermal expansivities for the two materials. Alright. Now, first condition, it said that the steel rod has the same length and area as the copper. So area of, let A be the area was not given. So let A be the area of the bars. So let A be the area of the bars. So area of steel, let's call that AS is simply equal to A, because lighting A represents the area. So the area of steel is simply A. Meanwhile, area of copper, AC is simply 2 times A, because we have two copper bars, first copper and second copper. So the sum of the two areas, the area of this and the area of this, simply give us 2 times the area, because the two coppers are the same. So since they are 2 in number, it means that area is 2. So we have that as 2A. Alright, so we are given from the condition which says that, or from the first question which says that a steel bar is placed between two copper bars, each having the same area and length as the steel bar. So the areas are the same. So if this is the area, if A is the area, then area of steel is simply what A, and area of the copper is simply 2A. Now, since the areas are the same, it means that, okay, let's, we've gotten that from the Alright, let's just keep that for the areas. Okay. Now, recall we said for a compound bar or a composite bar subjected to temperature, that the sum of the strain, so the strain of copper plus the strain of steel is simply the thermal expansivity of the higher material and the thermal expansivity of the lower material times the change in temperature T2 minus T1. So we are here. Meanwhile, okay, so this strain of copper plus strain of steel is now equal to the thermal expansivity of the higher material is simply with 0.000175. This has a higher thermal expansivity, which is copper. So we have 0.000175 minus thermal expansivity of the lower material, which is this. So we have 0.000012 times the change in temperature. T2 is given us, which is the final temperature, 315 degrees Celsius minus 15 degrees Celsius. So we have 315 minus 15 degrees Celsius. Okay? So EC plus ES is now equal to 0.000175 minus 0.00015 gives us 5.5 by 10 to the power minus 6 times 315 minus 15 gives us 300. Okay, so the strain of copper plus strain of steel is now equal to 5.5 by 10 to the minus 6 times 300 actually gives us 1.65 by 10 to the power minus 3. Okay, so let's call this equation 1. Now recall, we said that strain is simply stress all over Young's modulus. So it means in place of strain of copper, I will simply have stress of copper over Young's modulus of copper plus stress of steel over Young's modulus of steel, and that's equal to 1.65 by 10 to the power of minus 10. So we'll have this. Okay, also, let's call this equation 2. Let's call that equation 2. Okay. Okay, now looking at equation 2, of course we know the Young's modulus of copper and we know the Young's modulus of steel. So we can simply put in their values. The Young's modulus of steel is 210 kilonewtons per meter, while that of copper is simply 110 kilonewtons per meter. So we can substitute that in equation 2, and we are going to have the stress of steel over Young's modulus of steel or stress of copper, whichever way, stress of steel over Young's modulus of steel, which is 210 by 10 to the power of 9, plus stress of copper over Young's modulus of copper, which is 110 by 10 to the power of 9, is now equal to 1.65 by 10 to the power of minus 3. Okay, so we can call this equation. We can call this equation 3. Okay. Now recall that from the load equation, I said that after employing the strain equation, the next thing to employ is the load equation. And in the load equation, the pull by the material with higher thermal expansivity is equal by the push on the material with lower thermal expansivity. So that simply means the load of steel is equal to the load of copper. But also remember that I said that load is simply stress times area. So that means now that in place of steel, load of steel is simply stress of steel times area of steel, and that's equal to stress of copper times area of copper. But from the condition that was given to us, we have that the area of steel is simply A, and the area of copper is simply 2 times A. So if that's the case, then in place of AS, which is the area of steel, we simply have stress of steel times A, which is area of steel, and that's equal to stress of copper times, in place of area of copper, we simply have 2 times A. Alright, so notice that A can actually strike A from this side. So it might imply that the stress of steel is simply 2 times the stress of copper. So you can simply call this equation 4. Alright, so in place of stress of steel in equation 3, we can simply replace with stress 2 times stress of copper. So the equation becomes very easy and simplified. So we substitute now equation 4 into equation 3. And if we do that, we are going to have, in place of stress of steel, we simply have 2 times stress of copper. So 2 sigma c all over 210 by 10 to the power of 9 plus sigma c all over 110 by 10 to the power of 9. That's equal to 1.65 by 10 to the power of negative 3. Alright, so if I have that, let me now factorize. If I factorize, of course, sigma c is common, so you can factorize it. You have sigma c into, this remains 2 over 210 by 10 to the power of 9 plus this remains 1 over 110 by 10 to the power of 9. That's equal to 1.65 by 10 to the power of negative 3. Okay. Sigma c is now into 2 over 210 by 10 to the power of 9 will give us 9.52 by 10 to the power of negative 12 plus 1 over 110 by 10 to the power of 9 will give us 9.09 by 10 to the power of negative 12. And that's equal to 1.65 by 10 to the power of negative 3. Okay? So 9.52 exponential minus 12 plus 9.09 exponential minus 12 simply give us. So sigma c into 9.52 by 10 to the power of minus 12 plus 9.09 by 10 to the power of minus 12 is simply 1.861 by 10 to the power of minus 11. That's equal to 1.65 by 10 to the power of minus 3. Alright, so divide both sides by 1.861 exponential minus 11 to find sigma c, which is stress induced in the copper bar. Okay, so stress induced in the copper bar is simply 1.65 exponential minus 3 divides 1.861 exponential minus 11. So that will simply give us the stress in the copper bar to be approximately 88 meganewtons per meter square. So you have that. Now recall from equation 2. Recall from 2. We said that the stress induced in the steel is 2 times the stress induced in the copper. Sorry, that's equation 4. Is from equation 4. Okay, that's equation 4. So the stress induced in the steel is 2 times the stress induced in the copper. So that means stress in steel is simply 2 times 88 meganewtons. And that's equal to 176 meganewtons per meter square. Alright guys, that's the stress. Those are the stresses induced in the copper rod and in the steel rod. Alright, so next question says we should determine the original length of the bar. Okay, so we are given increase in length due to the temperature of 215 degrees Celsius. There was an increase in length of 1.5 millimeter. Okay. Alright, so we are going to do this from 2 angles. I will show you how to do it from 2 angles. I will do the first one and then maybe you can carry out the second one and confirm just to cross check the answers. Alright, so recall that when I started the analysis for thermal stress, when I started the explanation for thermal stress, I said that whenever a particular material is subjected to a temperature stress, then the strain of whenever a particular material is subjected to temperature, then the strain on the material, let's say for copper, strain of copper is simply, since copper has a higher thermal expansivity, it is simply going to be the thermal expansivity of copper, okay, times the change in temperature T2 minus T1, okay, minus the common strain, okay. So we're going to employ this now to solve. So we're going to see that if we decide to make the common strain subject of the formula by simply putting the common strain outside here, or if you don't do that as well, still the same, recall that, okay, strain of copper is simply the stress of copper all over Young's modulus of copper. So we are going to have that this becomes stress of copper over Young's modulus of copper, and that's equal to thermal expansivity for the copper material times difference in temperature T2 minus T1 minus common strain. Okay. Now the stress of copper was determined as 88 meganewtons, as 88 by 10 to the power of 6 divided by Young's modulus of copper was given as 110 by 10 to the power of 9. Okay, and that's equal to the thermal expansivity of copper was given as 0.0000175 by the difference in temperature is simply 315 minus 15, okay, minus the common strain, okay. So 88 by 10 to the power of 6 divided by 110 by 10 to the power of 9 will actually give us 8.05 by 10 to the power of minus 4, and that's equal to 0.0000175 0.0000175 by 315 minus 15 is actually like 300 minus the common strain. So I'll have 8.05 by 10 to the power of minus 4 to be equal to this by 300 is actually 5.25 by 10 to the power of minus 3 minus the common strain, okay. So if I decide to make the common strain subject to the formula, so let's then negative minus strain over to this side of the equation. Negative sign positive and equal to sign becomes positive. So we're going to have common strain is now equal to, so we have here left 5.25 by 10 to the power of negative 3. Now if you send this man over to this side, positive and equal to sign becomes negative, so we have minus 8.05 by 10 to the power of minus 4. So the common strain itself is actually now equal to 4.44 by 10 to the power of negative 3. So this becomes the common strain. But recall that strain itself is simply change in length all over original length. And the change in length was given to us is also called the increase in length. Increase in length of 1.5 millimeter, which we call 1.5 by 10 to the power. Okay? But change in length delta L, we obtain this as 1.5 by 10 to the power of negative 3 millimeters. Alright? So that means strain, which we got as 4.44 by 10 to the power of minus 3 is now equal to change in length 1.5 by 10 to the power of minus 3 all over original length. And the question is to find the original length. So making the original length subject of the formula, that simply implies that length is simply 1.5 by 10 to the power of negative 3 divided by 4.4 by 10 to the power of minus 3. So that simply means that the original length is simply 0.34 in meters. So that gives us the original length. Okay, so you can also try you can also try with the second method. Let me wipe this side. So the material with the lower thermal expansivity, from what I explained in the previous video, I explained that the material with lower thermal expansivity, okay, let's for still have lower thermal expansivity. The strain is now equal to the common strain minus the thermal expansivity of steel and the change in temperature, which is T2 minus C1. So you can as well employ the same equation. The strength of steel simply represents the stress of steel all over young produce of steel. So this is equal to the common strain minus the thermal expansivity of copper, of steel times change in temperature T2 minus C1. So you can see apply this equation, make the common strain solve the formula and solve, and you're still going to obtain the same result. Alright guys, I hope you find that video very interesting. Please do well to like, share, and then comment your thoughts in the comment section. Ask any question at all, and I promise to answer you. I'll see you in the next video. Don't forget to subscribe to the channel, and of course, I'll see you in the next video with wonderful questions on thermal stress. In the meantime, stay safe. Thanks and cheers.